Hi everyone, this is the Hungry Math Professor here, and welcome to my channel. And today I want to discuss a research paper that was actually published fairly recently called How the Continuum Hypothesis Could Have Been a Fundamental Axiom by Joel David Hamkins, who is a professor of set theory and is very interested in philosophy at Notre Dame. This paper was published in the Journal for the Philosophy of Mathematics in 2024. So last summer, I think. So it's a super recent paper, and I find it very interesting. And I've done several videos where I talk about the continuum hypothesis. So if you still don't know what the continuum hypothesis is, then I would encourage you to watch several of those videos. Depending on what you already understand, you may be able to skip some of them. But if you don't know, how to determine the cardinality of two infinite sets being the same or different, then you may need to go back and watch several of those videos, but they're all there on my channel already. And so I'll link to those videos so that you can understand what the continuum hypothesis is. There's several ways to state it. Some are sort of more general set theory ways of saying it, but I stick here to the way of stating it that's solely in terms of the real numbers. So you can say the continuum hypothesis that every infinite subset of the real numbers, its cardinality has to either be that of the cardinality of the natural numbers, which we call countably infinite, or has to be the cardinality of the real numbers, so that there is no cardinality in between when it comes to subsets of the real numbers. When you state this in set theory, you usually say that if you look at the size of the power set of the natural numbers, which we call 2 to the aleph naught, then it's equivalent to the next cardinal, the next size of infinite sets. So that's how you usually say this in set theory. Basically, that the size of the real numbers is the next cardinal, the next largest size of infinity that you can have after the natural numbers. Okay, so that's what the continuum hypothesis is. And it's important to this thought experiment to know that under the current way of thinking about, or what we know about ZFC, is that the continuum hypothesis is not decidable one way or the other in the established, foundation for mathematics, Zermelo-Fraenkel's set theory. That with the axiom of choice, which is generally used as the foundation of mathematics at this point. So that means that you can assume the continuum hypothesis or you can assume not the continuum hypothesis, and you will not lead to any contradictions in Zermelo-Fraenkel's set theory with the axiom of choice. So it's a good example of an undecidable statement, demonstrating that Gödel's incompleteness theorem applies to actual results that mathematicians care about. I would argue that the continuum hypothesis, especially when you state it in terms of the real numbers, is an actual question that mathematicians care about. I'm interested in whether there are subsets of the real numbers whose cardinality is strictly between the natural numbers and the real numbers. That would be an interesting result, right? Or if it's not true, it would be an interesting result. And the point is that given, ZFC, we cannot decide one way or the other. So there's an actual mathematical question about the real numbers, for instance, which we cannot decide. Okay, now that's not the point of this paper. That's something that's already well known, especially in set theory. So that's not the goal. And instead, the goal is to take us on a thought experiment. Now, before I go to that thought experiment, it should just be stated that even though the continuum hypothesis is not decided in ZFC set theory, there are still set theorists and philosophers who will try to argue for how it can be decided, right? So there are some in the set theory community who will argue that we just need to find what Hampkins calls this dream solution, which is we'll just find another axiom that we can add to ZFC, that when you add this axiom, it implies the continuum hypothesis, or possibly it implies the opposite of the continuum hypothesis. And this so-called dream axiom that we add will be universally accepted in the math community as being correct and being desirable to add to the axioms. And so in that way, we will decide the continuum hypothesis as either true or false by adding some other axiom which is somehow so natural that no one will want to disagree, right? That, and I think this is why he calls it a dream solution. That is hard to imagine. I think. I mean, I'm not saying it's impossible. I think if you came up with an axiom which had enough interesting consequences for mathematicians, it's certainly possible that we could accept it. So I don't think this is an impossible thing, but it does seem difficult to imagine to some degree that you would come up with an axiom like that that was universally accepted, especially given how, for the most part, we can do mathematics in ZFC without running into many problems. So it's just it's yeah, anyway, but that's just one way of imagining a way of deciding this question of whether the continuum hypothesis is true or not. Okay, but then there's another way, which is sort of Hampkins, I think, preferred way of thinking about this, which is his pluralistic multiverse view. I will do another video on his multiverse view of set theory because I find this very interesting. I'm just going to mention it here. And in Hampkins' view, you don't decide the continuum hypothesis by fixing sort of one axiomization which decides the continuum hypothesis or not. Instead, for him, you imagine that you take ZFC and then you imagine that there is just this multiverse of different set theories which are somehow class models of ZFC. And in those different class models of ZFC, sometimes the continuum hypothesis is true and sometimes it's false. And that's just what it is to decide the continuum hypothesis is that in certain models, certain class models of ZFC, the continuum hypothesis holds. And in other class models of ZFC, the continuum hypothesis does not hold. And that's just all it is to deciding it. And he likens this to the parallel postulate in geometry, where you don't ask to come up with an axiom which decides the parallel postulate. That just doesn't make sense. Instead, you study the geometries where the parallel postulate is true, you know, the Euclidean geometry, and you study the geometries where it's false, and you want to study all these different geometries, right? So he's arguing that we should think of set theory in the same way, and we should think of the continuum hypothesis as being analogous to the parallel postulate. Okay, I've already talked quite a bit about that, and I want to do a whole nother video about it. So let me just leave it there. But the point is that there are several ways that one could try to address the undecidability of the continuum hypothesis. Now, in this paper, he's going to take us on a different thought experiment to decide the truth or falsity of the continuum hypothesis. And I really enjoy this thought experiment because it also forces you to turn the dials on how axioms of set theory are established to begin with. It makes you think about why ZFC axioms are established as they are today, and whether we should really think about them as solid as they are, or whether we should think about them in some degree as something we've just sort of landed on as a something that works for mathematics. Anyway, I'll say more about that as we go through. So, what's the thought experiment? So, we need to go back to the 18th century when Newton and Leibniz introduced calculus. And it's sort of famous at this point that we know that when Newton and Leibniz introduced calculus, they're using these things called infinitesimals to talk about basically derivatives. But they're not very careful or rigorous about what infinitesimals are. And it's interesting because a lot of their calculations that they do with infinitesimals, these things that they describe as being somehow infinitely small, whatever that means, they do a lot of calculations that are correct, regardless of not having a very rigorous treatment of them. But as the history goes, they are other people, so, famously Berkeley, sort of make fun of these definitions and make fun of the lack of rigor and the lack of foundation that they have for these things. Berkeley famously calls these infinitesimals the ghosts of departed quantities, where he's trying to sarcastically talk about how, nonsensical these crazy things are, and in mathematics should be much more careful than that, right? And so in Hampkin's thought experiment, we need to imagine that Newton and Leibniz, when they introduce infinitesimals, also introduce a much more careful treatment of them than they did at the time. And just in case you don't know this, now we have a completely careful characterization of what infinitesimals are. This is called non-standard analysis on the hyperreal numbers, and non-standard analysis was worked out by Abraham Robinson in the 1960s, and we now know that this can be done. And so we should imagine that maybe Newton and Leibniz don't like completely establish all the properties of non-standard analysis and hyperreal numbers or anything like that, but that they start the journey of doing that right from the very beginning, more so than they actually did in history. So he gives a few sort of properties that they should understand. But for one, they should start to talk about the hyperreals as being the real numbers with these sort of clouds of infinitesimal around every single real number. So around every single real number, these like clouds of infinitely small numbers. Now, if you say it like that, again, you're going to be made fun of. So I'm just describing it to you. But the point is that they lay down a theory, or at least start to lay down a theory for how this can be made rigorous right from the very beginning. And also, he wants them to formulate something like what's called the transfer principle now, where we have the real numbers and then we wind up extending it to the hyperreal numbers, where we think of the real numbers as being now a subset of the hyperreals, where the hyperreals have all these infinitesimals in them. And we want to have what we call the transfer principle from model theory, which says that like any statement which can be made in the real numbers, in the language of the real numbers, will still be true in the hyperreal numbers. And if you want a more precise statements of all these things, I can point you to places where you can dive into the details. But via something like a YouTube video, I'm just going to give you the ideas. But in more technical language, we say that the hyperreals are an elementary extension of the real numbers and as real closed fields. So, what is a real closed field? Well, it's an ordered field like we're used to from analysis, but instead of saying that it's a complete order field, which is what we typically do in analysis, but that requires second order logic or can be done inside of ZFC set theory. But instead, we say that it's an ordered field where every positive number has a square root and every odd degree polynomial has a root. We say odd degree polynomial because we only want to add the real roots. And if you have an odd degree polynomial, it could be the case that an even number of almost all the roots are complex, but there has to be one real one because it's odd degree and complex roots come in pairs. So anyway, we this is a way of trying to complete them, but do it in an algebraic way. So we call that a real closed field. So the point is that the real numbers and the hyperreal numbers are both examples of real closed fields, and the hyperreal numbers are what's called an elementary extension of the real numbers because any statement you can make about the real numbers in the language of real closed fields will also be true of the hyperreal numbers. So the truth or false of these statements will be the same in both fields. Okay, I've said quite a bit about that. I think, again, all these things that I talk about today can be dived into much more deeply. I just want to give you the idea. So, again, for the thought experiment, we have to imagine that Newton and Leibniz have at least started us down the road of discussing the hyperreal numbers as the extension of the real numbers, where we add all these infinitesimals in around every single real number. Okay. And so the point is that he's trying to argue if that happened, then as the history of mathematics progresses, the hyperreals would become what we call like a standard mathematical structure, right? So I think any mathematician will agree that the natural numbers, the integers, the rational numbers, the real numbers, and the complex numbers are what we call standard mathematical structures. There are a ton more mathematical structures other than those. And depending on what field of mathematics you find yourself in, you may consider other structures to be fundamental. But I think we would all agree that if we're talking about all mathematicians as a community, then these objects, the naturals, the integers, the rationals, the reals, and the complex numbers, are certainly objects that we would all agree are fundamental, even if we don't work with them very much on a regular basis. And so what he's arguing is that the hyperreals would become another example of a fundamental mathematical structure that every mathematician would just say, you know what, the hyperreal numbers are just as important as the real numbers, as the complex numbers, and so on and so forth. Okay, so at this point in the thought experiment, in the historical development, the hyperreals become a fundamental object. So we say maybe like in the 19th century, it becomes like everyday knowledge that the hyperreals are a reasonable mathematical structure and becomes such a part of mathematical discussions that we all sort of agree it is an important thing to have. So the next point in the thought experiment is to look at the philosophical position called structuralism, which I argue and many I think people say this, is that this is sort of just the default position that mathematicians take without even knowing that they're taking somewhat of a philosophical position. Though it's also just so baked into mathematical practice, it's a very natural thing to do, which is to say that if you ask me what are the natural numbers or what are the real numbers, I'm going to give you certain properties that I want the natural numbers or the real numbers to satisfy. And then I'm going to say any isomorphic thing which has those properties is what I mean by the natural numbers. So, for example, I'll do this for the real numbers because that's the most close to home for me. If you ask someone, what are the real numbers? We say, well, there's several ways to construct them. You can construct them using Cauchy sequences from the rationals, or you can construct them from Dedekind cuts from the rationals. But what the real numbers are is, anything that can be constructed which satisfies, and it's a complete ordered field. And now what makes that make sense is that there's a categoricity result which says that any two complete ordered fields have to be isomorphic, order isomorphic. And so that's why I'm justified in saying anything you can construct which satisfies being a complete ordered field is what I mean by the real numbers, because it'll be isomorphic to anything else that you construct that's a complete ordered field, right? So instead of pointing to a specific construction and saying that's what the real numbers are, no, no, no. Structuralism says I just point to the isomorphism class of complete ordered fields, and anything in that isomorphism class is what the real numbers are. And so, in sense, real numbers are just the class of things that are isomorphic, right? And this is how mathematicians think. When you talk about groups, we're talking about anything which satisfies the group axioms. And if you put enough properties on a group, then you'll eventually get one group, right? So if you talk about groups and you talk about cyclic groups of size 100, now there's only one cyclic group of size 100, but I have to say up to isomorphism because there's many different ways you can construct a cyclic group of order 100, but up to isomorphism, they're all the same, right? And so we don't bother with, you know, just properties of any particular construction. We want to study what is common to everything in that isomorphism class. Okay. So, but what's important to that, if you want to have this structuralist approach, is that you need to have a categoricity result, meaning you need to know that there's only one of these things up to isomorphism. So, another part of the thought experiment is we want to assume that by around the early 20th century, we have categoricity results for the natural numbers, the integers, the rationals, the reals, and the complex numbers inside of just in time for the developments of set theory, basically. So this is part of his thought experiment, right? It's a fun little historical thought experiment. So at this point in time, we're imagining that all the fundamental objects, standard structures like the naturals, the integers, the rationals, and the reals, and the complex numbers have a categoricity result saying that there's only one up to isomorphism satisfying certain properties. But we don't have yet a categoricity result for the hyperreal numbers that are used for non-standard analysis. But of course, in this thought experiment, the hyperreal numbers are extremely important to us as a mathematical community. So we want a categoricity result. Okay, so now we're in the early 20th century, and Zermelo and Frankel, and we should imagine other people, some fictitious people, because it's the thought experiment, are working on set theory and are trying to establish axioms for set theory. Let's imagine that they come up with CFC as axioms for set theory, but because we want the hyperreals to be categorical, want them to be unique up to isomorphism, we are looking for an axiom which will do that, right? So we have ZFC. It's I should just tell you that ZFC is not enough to determine the hyperreal numbers up to isomorphism. This is something Hamkins talks about in the paper. It was shown it was shown that you can't have a categoricity result. So categoricity is not possible in ZFC alone. This was showed by Judith Reutemann in 1982, that if you take ZFC and assume that you can have basically non-isomorphic hyperreal fields, so that there are more than one field that would satisfy what it means to do non-standard analysis in this sort of not so rigorous treatment, and they would not be isomorphic, so it would not be categorical, and that would kind of bother the community because we want the hyperreals to be sort of a unique thing that we can point to. So what he brings up is that there's this result which shows that basically in order to determine the categoricity of the hyperreals, you have to have the continuum hypothesis. And so that lends credence to wanting to assume the continuum hypothesis as being true. And so we might have adopted ZFC plus the continuum hypothesis as the axioms of set theory so that we can determine the hyperreals as categorical. And we want to do that because of how calculus in this imagined thought experiment has progressed. And again, I just want to emphasize that the point is that you can't do it without ZFC. So if you assume ZFC and the opposite of the continuum hypothesis, then you will find that you have these non-isomorphic hyperreal fields, both of which can play the role that you need for non-standard analysis, and so it would not be categorical. Okay, so now he goes into a little bit of discussion of, you know, now continuum hypothesis gets on the list of fundamental axioms. And so the point is that, the reason why it gets on the list is because it has all this extrinsic support, meaning it has support from what we want to be true about mathematics. In this thought experiment, we want the hyperreals to be a unique sort of object up to isomorphism because we're using it to do calculus. And so there's a lot of external support for the continuum hypothesis. And you might say, oh, yeah, but maybe that's not the right way things should progress. But at this point, he points to the fact that this is basically how the axiom of choice gets a lot of extrinsic support. That, without the axiom of choice, there's a result that shows that there can be several different algebraic closures of the rational numbers inside of Zermelo-Fraenkel set theory without the axiom of choice. And there could be a countable one and an uncountable one, so they're not isomorphic. And this is very undesirable from the mathematical community's perspective because for us, the complex numbers have become an essential part of mathematics, and we don't want there to be multiple algebraic closures of the rationals. We want the complex numbers up to isomorphism to be the only algebraic closure of the rationals. And so that gives a lot of extrinsic support for the axiom of choice. Then he also mentions that there's intrinsic support, meaning like if you just study set theory with the axiom of choice, there are lots of results that show that this is a reasonable thing to do. But I think part of his point here is that you know not all mathematicians are set theorists, so not all mathematicians are always thinking about all these internal reasons for the axioms to be the way they are. Most of us are concerned with the extrinsic, um, you know, what follows from these axioms. We're very much interested in that. Don't get me wrong. I think if you hold our feet to the fire and ask us to study set theory, or if we're like back in the early 20th century or something, we're going to care about the internal consequences as well. But I think as a working mathematician, you care a lot about the extrinsic support or the consequences of these axioms and what they mean for what you can do in mathematics. And so, um, it's an interesting argument for why we might believe that the axiom of choice is true. Certainly, mathematicians like what we can do with the axiom of choice, and we feel quite handcuffed if we don't have the axiom of choice. We feel like we can't do a lot of things in mathematics that we feel like we should be able to do. And he's arguing that if we establish calculus using the hyperreals and non-standard analysis, much earlier on in the 19th into 20th century, then we would feel the same way about the hyperreal numbers, and hence we would feel like we want to add the continuum hypothesis as an axiom. And he also talks about how, like, if the epsilon delta definition, it would eventually be probably discovered, but it would become more sort of after this non-standard analysis approach or hyperreal approach, and but we would probably not emphasize it very much because we'd see it as unnecessarily complicated. And he just talks about how like he thinks the current hesitancy toward non-standard analysis is attributed to the lack of categoricity. Now here I'm not so sure if I agree with that claim. Um, I mean, I think probably the reason why we don't do non-standard analysis has more to just do with the fact that the epsilon delta definition is so established in the history and so established in the literature. And something else I'd like to see is, so there's a whole calculus textbook where they use non-standard analysis to teach undergrad students calculus, which is an interesting project. I can point you to this textbook if you've never heard of it, by Keisler in 2000. It's called Elementary Calculus: An Infinitesimal Approach. But just having an elementary calculus textbook that uses infinitesimals is not enough. We would need to look and see, like, what does differential equations look like using non-standard analysis? And what does partial differential equations look like? What does functional analysis look like? Like, what are all these different things look like in the terms of functional in the if you use non-standard analysis? How does that simplify things? How does calculus of variations look in that setting? Perhaps it doesn't change all that much once you establish derivatives using non-standard analysis. You're basically going to use those derivatives to do all the things that I talked about, which are, differential equations, partial differential equations, and functional analysis and calculus of variations. Basically, all these things are building off of the definition of derivative. But in order for non-standard analysis to become more universally accepted or more used in practice, you would need to see what all those different fields look like in the non-standard analysis approach. And the other issue I think with non-standard analysis is just that you have to introduce this very abstract object to students, and I think we are worried about how students might react to this extremely abstract object, even though in practice it makes the calculations much simpler. In any case, I don't want to say exactly why. I don't know that I know exactly why we don't adopt non-standard analysis. I think it's probably an inertia thing, which is kind of what I've already said. Inertia in the sense that we've already been using epsilon delta for so long, we're all used to it, we're all happy with it, and we're just going to keep teaching students it that way because that's what we're used to. It's probably something like that. But I'm just not so convinced that the hesitancy is because of a lack of categoricity. Though I agree with Hampkins that if it was categorical, if we knew it was categorical from earlier in history, it's possible that we would have adopted it. And I agree with his entire thought experiment that it's possible that things could have gone this way. It does seem a little unlikely that Newton and Leibniz, given the history that we know, would have presented something rigorous like the hyperreals, but it's possible they could have sort of at least pushed us down that road more convincingly from the very beginning, with trying to make the hyperreal numbers more carefully rigorous from the beginning, more infinitesimals rigorous from the beginning. In any case, what I like about this paper is it points to the fact that basically the axioms of set theory are well established and do produce very reasonable consequences, as we are very well aware of at this point. Set theory is a fairly well understood field at this point. There are lots of set theorists keep studying these things. And so I'm not saying that these axioms are completely arbitrary or anything like that. We have lots of evidence, both intrinsic and extrinsic, for them. But I do think it's important to reflect on the fact that at least some of these axioms, like the less basic ones, like the axiom of choice, are the kinds of things that could have easily not been included if mathematics developed a different way. And so also the continuum hypothesis could easily be included as a fundamental axiom if history developed a different way. And it just makes you think about, you know, what does the foundation of mathematics actually do for us? Does it make mathematics sort of absolutely certain, or does it make mathematics completely on a firm foundation? I think it does. What it does do for us is fix exactly what it is that we are talking about, right? When we do mathematics as an entire community, we could say that what we're doing is studying the consequences of ZFC set theory, and it does fix the discipline in that sense, and it does provide a foundation in that sense, but it does not necessarily completely get rid of any philosophical questions about the certainty of mathematics. And it's also possible, for all we know, that at some point along the way, we're going to find some, inconsistency in ZFC. I mean, I think it feels very unlikely, but anytime I say it feels unlikely, it's sort of a belief or a faith that I have more than something we can prove. We can't prove that. And it's possible. And if that happened, then we would amend the axioms, or we amend the foundation some way, and we'd have a new crisis in the foundations of mathematics. But I don't think that if that happened, we would assume that mathematics is wrong. We would just assume that the foundation is wrong, and we would look for different axioms, or we would try to amend the axioms. And anyway, I'm not saying too much more here, but I do think it's a good reflection to have as a mathematician about the foundations of mathematics. That mathematics, I think, is a completely solid field in a lot of and I'm not really trying to cast doubt on that. But despite the fact that mathematics, I think, is a completely solid field, it's not exactly easy to say exactly what it means to be solid, or what it means to be certain, or anything like that. At the very fundamental level, everything that we do as human beings requires like a little bit of just a smidgen of faith or belief and contingency, I think. But in any case, I think we could say with absolute confidence that mathematics at this point is mostly seen as the consequences of ZFC set theory. And even though, as a working mathematician in geometric analysis, I almost never go down to the depths of ZFC, I think almost every working mathematician, if you push them to it, would say, well, yeah, the foundations of mathematics is ZFC. And it's interesting to think about how, if history went a different way, we may have wanted to say ZFC plus the continuum hypothesis. in order to make the hyperreals a categorical object. Okay, I hope you found this discussing interesting. I hope I didn't go on for too long there at the end. I will point you to the paper that I'm talking about, as well as some other videos that I've done that can help you understand this. And I plan on doing other videos related to set theory, multi-use view of set theory in Hamkins. So please like, comment, and subscribe, and I hope to see you at another video.